All right, good day, guys. Welcome again to my channel. I am Joshua, the designer. All right, today we'll be taking another step forward on the design of steel connections. All right, in the last tutorial, I was able to show onto us how to go about the design of bolt connections, and I showed to us categorically that the design strength of a bolt connection could either be in shear capacity or in its bearing capacity. And from the example we took in the last tutorial, we obtained the value for our shear capacity, and that's for our bearing capacity. And comparing for the shear capacity and the bearing capacity, we could conclude that the strength of this particular connection is in its shear capacity. All right, so the shear capacity governs for this particular um, connection. Okay, so to go further from here, we would want to take another insight. All right, so for this, shear capacity governs, so this would be the strength of that connection. All right, so in today's tutorial I'll be showing to us about the double shear connection. We've done single shear connection, and that is exactly what we've done in the last tutorial. Okay, so I'd like that you go with me as I take you through the double shear connection. All right, looking at this first figure. All right, so we have that the first figure represents the single shear failure. All right, and what do we mean by single shear failure? It means that the connection only possesses a single failure plane, or the shear occurs in a single failure plane. All right, the shear occur in a single failure plane. That's just what a single shear failure means. For the double shear failure means that the shear occurs in a double plane. All right, in a double plane. So as you can see in the second figure that we have, that our connection would experience a double a failure in two planes. All right, failure in two planes. So, and this is what we have here in the second illustration. This is a single shear failure. All right, so and the single shear failure is exactly what we did in the last tutorial, and in today's tutorial I'm taking you through the double shear failure. All right, so let's just pay attention as we go through together. All right, so basically there are almost similar steps to solving single shear failure but mode and the double shear failure mode. I just need to point out one or two changes along the line so that we can get to know. All right, so from this would understand that our rule still remains, our consideration still remains that for any bolt connection, the strength of the connection either lies in the shear capacity or the bearing capacity. All right, so we're going to create a test for either the shear capacity or the bearing capacity, then compare the two results, then would make a conclusion on where the what the value of the shear capacity or the bearing capacity, which governs um, between the two. Okay, so as requested in this example, we have an example here on the screen. It says the lap joint similar to whatever example, that example you don't know. All right. All right, so there are two shear interfaces, meaning that this is a double shear failure mode. All right, so and there are four 20 diameter grade 8.8 black bolts. All right, the outer plates are 8 thick. The outer plates are those on the right here, as you can see, this and this. All right, so and the inner plate is 12 millimeter thick. That's the one on the left here. Okay, so they are all S275 steel. So we have to determine A and B as in the previous example. Okay, so I have already extracted what the A and B would be from the previous example. So we have to calculate for the minimum and the maximum edge and hand distances, just like we have done in the previous tutorial, that we extracted some from the code of practice. All right, so the minimum edge distance, everyone who had gone through the previous tutorial would not have an issue with this first one, seeing that we have treated this over and again. All right, so and we established in the previous tutorial that our big D is going to be the small d, which is the diameter of the bolt, plus, now depending on what diameter of bolt is, so if you can, so to not waste our time, you can refer to the last tutorial and see what you're going to add to your actual diameter of bolt to get your big D. All right, okay, so with reference to clause 6.2.2.4, all right, in our code of practice, you find that. So but for this diameter 20 mm, we're going to add 2 mm, so that's going to be 20 mm plus 2. Our big D is 22 mm, and that's what we're going to work with. So you need to check this code and go through the last tutorial to be clear on that. Okay, so this would give us 1.25 multiplied by 22, and this will be equals to 27.5 millimeters. All right, okay, so for the maximum edge distance we've done for the minimum. Now these formulas can be gotten from the code of practice, of course. If you have gone through the last tutorial that I made last week or whatever it is, you would be able to pick up this from the code of practice as easy as it is. 6.2.2.5 for reference sake. This also can be gotten from there. So the maximum edge distance will now be 11 T epsilon, and I showed to us what epsilon would mean in our last tutorial, which is 275 over py raised power 0.5. Okay, so if you need anything around that, you would we used the last tutorial. So the py for this, we have been given S275 steel, and the thickness of the plate, the maximum thickness of the plate we have here is 12 mm, which is less than 16 mm. So that means our py is still going to be 275. If you don't understand what I just said now, our last tutorial is just for you, so you can just go there and get back to joining us on track. All right, so we're good. That'll give us one. Okay, so if we are going to walk through now 11 thickness, the thickness of our plate. Now if you see now, we're having 8 mm outer plate, 12 mm inner plate. All right, so if you want to go by the larger plate, you use 12 then 1. All right, or if you want to go by the average of the two plates, you may have to use um, 10. That's 12 plus 8 divided by 2, that's 10. Oh, but then this seems to be more safer. All right, since we're using the larger plate, and some other people might want to use the least plate, whichever it's cool with you. All right, so this would give 132. If you are using the smaller thickness, that will be 88. If you're using the smaller thickness, which is 8 mm, all right, so that will be 88 mm. All right, so okay, that's good. So to move further, we have done for the edge distances, so we need the end this we need the what do I call it now, bolt spacing. All right, we need the bolt spacing. We have done the minimum and maximum edge distances. All right, and we have answered that question. So if you want to do further, as the code recommends, you may want to do the bolt minimum and maximum bolt spacing. Of course, this question did not ask us to do that, so we might not necessarily do that. But if you want to do that, use our last tutorial and find how to go about it. So we have answered the first query here. So we may want to move further to our next question, which is the bolt share. Okay, so just like we had shown in the last tutorial, that the way to calculate our share is in the code of practice. So we want to just create a reminder from our clause 6.3.2.1. All right, and do not forget that this is a double share plane. We are dealing with the double share failure mode here. All right, so that must be in our consideration. So from the code of practice clause 6.3.2.1, let's just see what's there. 6.3.2.1. all right, so this is the share capacity, which says ps equals to ps as. All right, so for the both share capacity, ps then equals to small ps as. All right, so our small ps is can be obtained from the table 30 of the code of practice. So you have to be close to your code of practice to get things done. All right, and the questions told to us that we're using 8.8 bolt grade. All right, so and which has an equivalent shear strength of 375. Okay, so 375. So our ps is 375 newton per meter square, multiplied by the area of the shear area of that bolt. All right, so which could be the tensile area, or if not specified, can be taken as the shank area. You can check that from the code of practice I showed in the last tutorial, and it's written just here. A is the shear area, A or AT, which is the tensile area. All right, to go further, let's just so the area of the 20 mm bolt, 245. All right, so for a double share capacity, this formula you have to add multiply by 2 because it's double. All right, so and that's why we have 2 multiplied by, do not forget that that makes the difference. Okay, so we have 183.75 kilonewton. This is well greater than or equals to 37.5 kilonewton, which is going to be the shear force, or the force acting on one bolt. How do I get that? If 150 kilonewton is acting on 4 bolts, 150 kilonewton acting to the right and to the left on 4 bolts. So when you do that, you have 37.5 kilonewton acting on a bolt. All right, so we are comparing the shear capacity of one bolt to the force that is being experienced, that the bolt is being subjected to. All right, so that's how we got that. Okay, so that solves the shear capacity. The next one is going to be the bearing, the bolt bearing. Okay, so from our clause 6.3.3.2, as I've shown in the last tutorial, we have bolt bearing to be obtained using this expression. Then our small d, which is the actual diameter of your bolt, multiplied by the thickness of your plate. All right, so we are using the inner plate, or the outer plate, so rather, multiplied by the bearing strength. So to obtain the bearing strength, you can check table 31 of your code of practice. Then that will give the bearing strength of the bolt. We are using bolt grade 8.8, which is 1000 newton per millimeter square. All right, so that's what we're going to be applying in this calculation. We'll have 1000 newton per millimeter square. Okay, so working this all through should give 160 kilonewton. Okay, which is well above 37.5 kilonewton. So you see that this is actually sufficient. This is sufficient in bearing also. Okay, so let's move ahead. The next one would be the plate bearing. The plate bearing for that connection, the plate bearing. Okay, so for plate bearing, we can check for clause 6.3.3.3. Okay, so we have for the 8 mm, we have the 8 mm outer plate, and there are two in numbers. All right, two in numbers. So we have the formula from that clause: kpbs tpbs, which must anyways be less than 0.5 kbs a tp pbs. All right, so in putting all through our values, we have 20 thickness of plate, we have 8, and pbs. If you check table 31 32, you find that pbs is supposed to be 460 for 8.8 grade. Okay, so this is going to be, and this is two numbers. Do not forget that you're going to apply the two into bracket. The result of this should give us 73.6 kilonewton. All right, so the result of that 73.6 multiplied by 2, you should have 147.2 kilonewton, which is still well greater than 37.5 kilonewton. All right, so for the 12 mm plate, which is the inner plate, which is one numbers. So PBS, still using the same formula: 1.0 multiplied by 20 multiplied by 12 multiplied by 460. All right, so that should give 110.4 kilonewton, which is well greater than 37. Sorry about that. 37.5 kilonewton. So this is still fine. This is still fine. So we've obtained um, plate bearing. So we're left with block shear capacity and plate tension capacity. Then from all of this, we'll be able to obtain what exactly is the strength of that connection, all right, that bolt grouping connection. All right, so the next will be the block shear. So for the block shear, you can check the clause 6.2.4, which would give you, let's check together. All right, for the benefit of those who would not know how to go about this. 6.2.4, we have 6.2.1, 6.2.4. Yeah, so this is what we have: a block shear failure. You see that now. So this is this formula that would use in getting the block shear. So we have PR is equals to 0.6 PYT in bracket LV plus KE in bracket LT minus KD, capital D T. All right, so the thickness of our plate, if you want to use the smaller one, fine. If you want to use the larger one, fine, or the average of the two, you'll still be fine. All right, so we have this to be 18 mm. We have LV. If you don't know what LV is, let's go back to our code: block shear. So you see what LV is, the vertical length. You see the LV and LT. All right, so those are in the code. So LV would be 25 mm. You have LT to be 25 mm. You have K to be 0.5. Alright, so if we put all this together, we have a PY ready to be 275 and our T to be 8. If you are comfortable with the average, you can use 10. So LV will be 25 plus KE, which is going to be 1.2. 1.2. LT is going to be 25. K is going to be 0.5. And D, as I said, is going to be 18. So the result of this should give 73 kilonewton. See that, which is quite okay. Now from this, I believe you want to stay close to your code so that you get where I obtain all this value. See, K is for 2 lines of bolt 2.5, for single line of bolt 0.5. So all these values are in your code, please. So you may want to check through and see how we got about some of these values in case you have questions. All right, so from here we can move further. So the last one from our question will be the plate tension capacity. The plate tension capacity. Okay, so and from our usual application, you may want to use our last video to obtain the plate tension capacity. Tension capacity. All right, and this will be our interactive section. I want you to do this and use the comment section and drop your results on plate tension capacity. If you have any questions that's touching double shear failure mode, I want you to just use the comment section, as I'll be there to answer to all of your questions, your queries, and your demand. All right, so thank you for staying around. If you are joining this video, joining my channel for the first time, I'd like that you subscribe to this channel, like this video. I'm Joshua the designer. See you again. Bye.